Suppose we want to know exactly when a visual stimulus appeared on our screen. A common method is to put a photodiode on the corner of the experiment display and flash a patch of white on the same video frame where the stimulus appears. The photodiode immediately registers the change in luminance and sends a signal, also called a trigger, to the receiving equipment. This is an effective and simple way to mark visual events in your recording stream. Now let's imagine this photodiode is sensitive to the color red. It can detect the 8-bit color value of a patch of red pixels, anywhere from 0 to 255. Instead of a single output, this photodiode has 8 channels of output. It can send 255 unique combinations of activity on these 8 channels. That's one unique trigger for each level of red detected. This high-resolution photodiode can signal multiple kinds of events on our display. One shade of red could serve as a trigger indicating the start of a specific condition or block, while another means it's the beginning of the response phase. We can even use unique shades of red to tell our recording system if the participant responded correctly or incorrectly on the previous trial. Unfortunately, photodiodes don't have this kind of resolution, and they have another big disadvantage. They're a pretty big distraction for the person looking at the screen. What if, instead of measuring the red value of the patch on the display, we measure it in the video data coming to the display? If we do this, that patch of red can be quite small, only a single pixel wide. We can then send our 8-bit signal to the receiver without any distractions on screen. This is the principle behind pixel mode. Because we send signals based on video data, there is a short delay between when these signals are sent and when the screen physically illuminates. If we know the value of this delay, we can use pixel mode as a reliable indicator of screen behavior. In the case of our VIEWPixx EEG, the delay between the pixel mode signal and pixel illumination is exactly 6 milliseconds. Pixel mode is a reliable, high-resolution, and zero-distraction method of sending video-based triggers to your recording equipment with microsecond precision. One of the nice features of pixel mode is that it is fully automated. It doesn't matter what experiment software you use to create your stimuli. If you can edit the value of that top left pixel of your stimulus display, you can use pixel mode. Most EEG systems have a maximum of 8 channels of input, or 8-bit resolution. This means they can receive up to 255 unique trigger values. Some systems have 16 or even 24 channels of input. In this case, we can also use the green and blue values of that pixel to extend our signal resolution to 2 to the power of 24 unique triggers. That's over 16 million unique trigger values. There's a few things to keep in mind when using pixel mode with our hardware. First, not all trigger cables are the same. While the DB25 port on the side of our devices looks a lot like a parallel port, it's not. It's wired differently. You should only use a cable specifically designed to serve as a trigger cable for our hardware. Never plug a random cable into any experiment hardware, even if the ports match. You could risk damaging your equipment. Finally, it's important to keep in mind that some software, graphics programs, and graphics cards can adjust the value of the pixel before it reaches your display. Common culprits are normalized color mapping, gamma correction, blending, anti-aliasing, or dithering. If your trigger values don't look quite like they should, investigate your experiment software to see if any of these are at play. If you run into issues, don't hesitate to contact our technical support team for assistance. We're happy to help. The contact link is in the description below.